go. All right.
There you go.
Okay, you guys missed a lot. I thought I was recording and I wasn't. Mostly we missed going over a couple of problems in the review packet. So find somebody and get the notes on that. But these are the new notes for today, and it looks like maybe it's going to work this time. Yeah?
I like that you're talking to us, so you're talking to us.
I know.
This is a new experience.
Okay. You're me. Inverse function. I am not going to do anything today that you haven't seen before. Okay, I may do it a different way, but I'm just going to remind you of what you're supposed to know about inverse functions. We're not going to do the derivatives of these yet. So suppose I have these two functions, and just two particular functions, nothing special about them. And I ask you to do the composite function f of g of x. Okay? All right, so that means that you're going to say 3x squared plus 1. Everybody remembers this? Okay, which is 9x squared plus 1. Okay, and then suppose I ask you to do g of f of x, then that is 3 times x squared plus 1, which is 3x squared plus 3. Okay, and the point of this is, one, to make sure you remember how to do composite functions, and two, to make sure that you remember that just if you pick any two random functions, f of g of x is not going to necessarily equal g of f of x. That, if you just pick any two functions, that's probably not going to happen. But if you pick the right two functions, let's do f of g of x, it would be the square root of x minus 1 squared plus 1 so f of g of x for this function is x, and if you do g of f of x for these two functions, with some slight domain issues here. Technically, the square root of x squared is the absolute value of x, okay? But we're going to just fudge over the absolute value part for right now. If you restrict the domain, then the answer is just x, okay? And when this happens, when f of g of x equals g of f of x, and they both equal x, when that happens, then we say that f and g are inverses of each other. Okay, this is coming back to everybody. Remembering this a little bit. There was an inverse notation that you had to know. We can say that the inverse of x, I'll say sometimes we use this. We use this to represent the inverse of f. It is slightly confusing notation because it looks like reciprocal notation. You just need to know that when you use that -1 raised up with function notation, that it does not mean reciprocal anymore, it means the inverse up. And the nice thing about it is it connects you directly back to the name of the original function. Sometimes you use two different names for one, R, F, and G inverses, or sometimes you use the F inverse notation. Okay? Everybody good with that? Okay, graphically. If AB is on f of x, then BA is on f inverse. Your very first introduction to inverse functions probably was just in switching the coordinates of the points. Okay, that's probably the very first thing that you did. Okay, when you do the graphs of a function and its inverse, there will be reflections about the straight line y equals x. The line y equals x is that nice line right through the origin, 45-degree angle, yes? So if I tell you that this is f of x, if I tell you that, you should be able to visually get an idea of what the inverse of f of x looks like by reflecting it about that line. And the idea would be to try to fold it, think of it as folded, and leaving the impression on the other side. And what it would look like is right straight across here, this, and then it would get closer and come back away. That would be f inverse. Y'all see that dotted line there, this thing right here, this little part right here, it's supposed to be a dotted line and failed. Okay. All the way across it, the points are equidistant from that y equals x line. So when this gets closer, see it gets closer right here, then it's going to be closer right there. When it starts to get further away, it starts to get further away, which is another helpful way in getting these drawn. Some of them are easy to draw, some of them are a little bit harder. A second to try to draw something that looks kind of like that. Give it a negative x-intercept and a positive y-intercept and have it cross through that line y equals x over here in the first quadrant. And then the trick is, can you visualize what the inverse of this function would look like? If you have actual points, you can actually flip the points and plot the flipped points, and that's helpful. So if it's on a piece of graph paper. But other than that, this point right here will convert into a point right over here. Yes? This point right here will convert into a point right over here. Just right straight across like that. So that x-intercept ends up on the y-axis, and the y-intercept ends up on the x-axis. And then this one, this is a nice point, isn't going to go anywhere. Okay, and sometimes that's enough to kind of get you started. Closer will be closer, further away will be further away. There's always some people that are better than at others than this, at this. Okay, it's just sounding familiar.
What? Oh, because the x and y is similar.
I don't know what that means. Oh, yes, yes, I got you, yes, because the x and the y are the same, so if you switch them, it's not going to change. Okay. The people who have difficulty visualizing this, it's just always helpful to have actual points, and then actually flip the points, and then usually it's okay. Now, a reminder that not all functions have inverses. Have inverse functions. Okay, so this is not a question of not having an inverse, it's a question of its inverse not being a function. And there's a super simple one, and that is this nice little easy f of x equals x squared. And if you do this graphically, the decreasing parts are always harder. People have a harder time drawing the decreasing parts and getting their inverse right. But the inverse of this would look like this. You see how that looks like the square root function right there? And when this part flips, and I'm not going to go over with you why it does this, but it comes over here. So you end up with a square root function on top, and then like a square root function on the bottom that's been flipped down. It's a parabola that's been turned sideways. And you can see that it's an inverse, but it's not a function. Yeah, what you have to do is restrict the domain. You have to pick which section of the function do you want to have an inverse, okay? So, and I'll get there, I think it's on the next page, okay? So one thing you have to remember is that a function has an inverse if and only if. Have we used this notation before, the IFF? Have y'all seen that? I can't remember if I showed you that. It means if and only if, okay? I'll give you a minute to jot that in, if and only if. Math people hate to write words, you know, we're always kind of short ways to write them. If and only if it's 1 to 1. And that means 1x takes you to exactly 1y. And it also means 1y takes you to exactly 1x. Okay? So functions only say that 1x can take you to exactly 1y. They allow two different x's to have the same y value. In order to have an inverse, that cannot be. And there's a really, really super easy way of telling that graphically, okay, or visually. The word is monotonic. The graph is monotonic, and this word means that it is strictly increasing or strictly decreasing. So if a function always increases or if it always decreases, then it will have an inverse function. Okay? And now here's the calculus connection. How do you tell if a function is increasing? Calculus. Not the second. First derivative. This means that f prime would have to be positive and f prime here would have to be negative. So one of the things you'll use calculus for is when you don't have a picture of it, is you will look at the function, take the function and decide if its derivative is always positive or always negative. Okay? And that's one of the things that'll happen. And that looks like this. You know, you remember about cubic functions. The basic cubic function, the basic one, y equals x cubed, looked like this. Do you remember that? But then a whole bunch of other ones bounced around like this. Okay, so and it can be kind of hard to tell when you just look at the function. So we're going to use calculus to tell what this thing does. F prime of x equals 3x squared plus 1. So if you look at that derivative, is that derivative ever negative? Square it, multiply it times 3, add 1. So f prime of x is always positive, therefore f of x will have an inverse. I need to add the word function to the end of that. F of x will have an inverse function. Okay, and then we could go about trying to find that inverse function if we wanted to. So that's what's required. Okay, another function. Make one little change. Oops, just x cubed. That looks like exponents. And the derivative of this is 3x squared minus 1. Okay. And you can tell pretty quickly by this that it is going to change. Sometimes it's going to be positive and sometimes it's going to be negative, okay? So you could find those places, but it is not always positive or always negative. Therefore, this function does not have an inverse function. An inverse exists, it's just not, it's not going to be a function, okay? So what we do when this happens, and I'm going to take one that's real easy to graph, sine of x. Does sine of x always increase or always decrease, or does it go up and down? Up and down. So does it have an inverse? No, it does not an inverse function. Okay, so what we do is we pick a section of the sine function, or of whatever function is, and we say we're only going to look at this section where it strictly increases, or where it strictly decreases. And we know we're studying trig last year. You did inverse trig functions, right? Arctan or sine with the -1 on it, the two different notations, yes? Right, don't panic, I'm not going over that right now. But at that point, you had to learn what were the restrictions on each of the trig functions, and there are some, to some degree, arbitrary. They're usually close to the origin. They are close to the origin. And you could pick other sections, and that would have been just as good. These are just the ones that were picked to be the standard. So for sine, we restrict the domain. And in this case, the domain would be from -pi/2 to pi/2. Then we would have an inverse function. Okay? So we'll come back and revisit that a little bit later on. Okay? All right. Find the inverse. Now, at this point, the only thing I've said that you didn't do last year was using the derivative to determine if it's increasing or decreasing. You did this by some other method last year. Look it on your calculator or something, okay? So I want to find the inverse, okay? Pretty sure you spent some time with this. I'm almost done. Okay, so the first thing you want to always notice about your function is what is its domain. So how do you do the domain of a square root function? Yeah, the inside stuff, and I've done this in Algebra 2 this year. I teach this to Algebra 2 every year, and by the time they get to calculus, they've forgotten the word for it. What's the stuff under the square root?
The radicand.
Very good. See, all you have to do is remember that there's a word for it. So you take the radicand, and you say that it must be greater than or equal to 0. We did domain review back at the beginning of the year, and this stuck a few people up. Okay, so the domain of this is x has to be greater than or equal to 3/2. Yes? Okay, it's nice to note the range of it. This is one that you should know. I don't care what you plug into this. It's always greater than 0. Y is greater than or equal to 0. Now, some of these are going to be all real numbers, okay? That is going to happen. Okay, so how do you actually solve this? Well, the first thing you do is you replace the f of x with a y, because it's easier to work with. And then different teachers and textbooks tell you to do this in two different orders. One method is to solve it for x and then switch the x and the y. And the other method is to switch the x and the y and then solve it for y. That's what I prefer to do. So I'm going to switch the x and the y. Now, why are you doing that? Well, because every point on an inverse switches the x and the y. Every single one of them. So I'm going to just switch the x and the y. Now, I've now made it into an inverse relation. I need to now turn it into function form again. So I need to solve for y. Take the square root of both sides. And the form of that does not matter. Either one of those is fine. Okay? And then I'm sorry?
Is that a 2?
It is a 2. And then the last thing would be to decide what you want to name this. And so for right now, we'll just name it f inverse. Whatever the function was called, we'll call this f inverse. Now, this function in and of itself hasn't got any restrictions on it. Like if I just talked about this function, this is a parabola, yes? Actually, it does have a little bit of a restriction because a parabola either opens up or it opens down. It either has a max or a min. But I don't have to worry about that because the domain and the range for this are going to come from the domain and the range from the original function. So the range in the original function becomes the domain in this function, okay? Even though you think you can plug anything into this, if you plug anything into this, you don't necessarily get functions out of it. Okay, and then the range was, I've forgotten, is it greater than or equal to 3/2? And these come from the f of x. Okay, y'all remember that? Yes? Okay, so your homework tonight is this, that's the second half of it. And the first half of it, I think, is 5 problems finding area. And I think there's 1 application problem where you have to read it and set up it says something, you know, dy dx is proportional to something, and, you know, we've done those before, the antiderivatives, only this one's probably going to have an ln when you take the antiderivative, and there are 5 of them. Does everybody understand? Okay. To the ladies who I'm sure are listening to this very carefully, you do need to get the notes from somebody. We went over a couple of problems from the review packet, but this is all of the new notes. Okay, that worked pretty well. Okay. Pause.